Hey everybody, how's it going?
Hello.
Good to see some of you again. It's nice to be back in AGI House. Unfortunately, I'm in Toronto where it's cold and raining. I'm sure it's beautiful there, but good to see some of you again. Thanks for having us. So I'm Austin. Sai's joining me as well. We're going to talk about what happens when you apply collective intelligence to an agent swarm. So the basic question or like the theme of this presentation is that like no breakthroughs throughout history have ever happened alone. Like every single one has stood on whatever has come before it. That's the overall theme of what we're talking about. And we had this question a few months ago, like, can a swarm of agents find breakthroughs? And as you've seen from the presentations today, like this is a hard problem because it's actually quite constrained. And what we discovered is that like research is basically a coordination problem at this point when you're trying to apply it to agents. And like the core problem is just that like agents are isolated and they're wasteful, right? Like if you think about like models get trained, they update weights, and then you've got this context window for these agents that are trying to apply what they can do. Like there's just limitations on how much information they can like operate over. And if you like draw the parallel to research teams, right, it's like you have all your schooling that you learned and understood, then you have like exactly what you're focused on, that's your context window. But then you don't just do the research alone, like you bounce it off of the ideas of others, and agents can't really do that well because they're pretty isolated and they can't manage state very well. And so we applied our harness to solve some pretty hard research problems. And our core thesis is that one agent acts, but many of them can compound together. And we proved this in the open. So last time we were here at AGI House, we were in the middle of running this experiment, which was taking like Karpathy's Autoresearch problem and applying it to swarms all over the world. And when this finally finished, when we finally stopped running this, like we had, I think it was 120 agents in total that did about 3,000 experiments. So that was like 5-minute runs of that auto research loop, and that was like a few dozen people that were paying like $2 an hour to rent Blackwells and run these GPUs, and all of them were able to contribute to this research project in the swarm. And I'll just like share kind of quickly like what that looks like. If you guys are you still am I showing a website right now, or am I still showing? Yeah,
Yeah,
okay.
it's the website.
Okay, sweet. So um like this is basically what we did, right? So like someone would come, they would run like a baseline, they would essentially run like the auto research code, and then over time, like there's some people in this room that I actually recognize that are probably some of these people that contributed to this. And then the agents would pick up whatever the best runs were, they would run the result again, and all of it was trying to optimize like validation BPP. And if you had a better result, then you wrote to the shared memory layer, which was on Ensue, and then all the other agents that came after you were able to take that result and use that as the new baseline, and then discover, essentially iterate on top of each other. And what we were able to achieve was pretty cool, right? Like we had hundreds of agents that were running in total, like, yeah, over 3,200 experiments, and like a really sweet leaderboard of people that were renting their own GPUs to contribute to this, which was awesome. And then since then, what we've been able to do, like we've applied this to solving really hard Putnam math problems. Like we had to build like best in class memory and retrieval in order to achieve this. Obviously, you can read more about like our the auto research itself. And then yeah, with like a couple of people in this room, I think I see like TMC and obviously like Steven, we collaborated and we worked on applying this to building kernels. So we were able to have like 6x performance improvements on Apple Silicon using the same swarm approach. And what I'm actually going to stop talking. I'm going to pass it over to Sai because we just applied this. We haven't actually released this paper yet. It's coming very, very soon. It's currently like it was just endorsed, and it's hopefully it'll be live in the next couple of days. But I'll actually just stop talking. I'll pass it over to Sai to talk through like our implementation of this TurboQuant kernel that was able to achieve like pretty amazing results over long conference inference. You're muted, Sai.
Sorry, guys. Okay, can you guys see my screen okay? Um,
Yeah, we can see it.
cool. Yeah, so we got really into the kernel optimization world of things. This was also kind of mentioned as a topic of interest during the AutoML talk. But this is a concrete experiment where we were able to run 128K size context window on a 64 gigabyte consumer Mac, like 2021 M1 Mac. And so, yeah, here were some of our numbers that we got from our agent swarm. This one was run over an experiment. I started the swarm. I did not pay attention all weekend, and by the end, I had a super fast kernel, and I was running Llama and Gemma 431B locally on my Mac, which was super cool. And so yeah, here are some numbers in particular. You'll notice one of the methods that we used for specifically memory compression was TurboQuant, and that received about 3.2x KV cache compression locally. And so I was just going to talk about a little bit about the agentic harness and setup that we used. It was surprisingly straightforward, and it was amazing to see the end result happen in such a short period of time. So usually, even with Autoresearch at home, as Austin showed, it's pretty straightforward. You have collaboration rules and guidelines. Our memory system is really the kind of foundation for a retrieval system. And so the way you apply this retrieval system is described in a collab MD, and a program MD kind of has the agentic loop along with kind of like a hierarchical memory taxonomy. Like the way to imagine this memory actually is very much like a file system. And so in your collaboration primitives, you can kind of index memory, really index data and organize it that in a way that allows your agents to really draw conclusions quickly and really sift through data efficiently. So yeah, here's one of our experiments. All of this agent memory is available. So if I look at this one experiment that ran, you would very quickly see, whoa, this is super funny. Gemma has some opinions about Pokemon. Anyway, yeah, this is basically like the memory that we were able to produce from this, again, in describing this kind of memory taxonomy. So once you have like descriptions for both of these, it's very simple to plug this into like an agent like Cloud Codex. And the agents themselves had a kind of like sub-agent system set up. So each of them, I think around 8 to 10 of them were orchestrators, and all of them churned forward with a goal to maximize breadth or like creativity. Basically, don't hill climb on diminishing return problems, try to find bigger issues that have huge potential for growth. And so having kind of a diverse set of agents, diverse set of roles helped with this significantly. For instance, like we had diagnosticians that would look at particular data or find metrics that were deemed relevant, and we would actually automatically create different auto research loops. So separate to the initial version of this experiment where there was a single auto research loop, we had many different auto research loops running in parallel on different metrics, different validation systems on top of plateau and reflection sort of analysis. So we actually had many of our agents would hold, say, statistical models, regression models, whatever, for the metrics that they were optimizing, and plateau detected. You have some reflection loops and things that would effectively stop the agent from wasting tokens on diminishing return type search frontier. So yeah, this is the loop. I've described it a bit so I can speed up. But yeah, that was kind of roughly what we built, and it yielded a very cool paper that we will release very soon. But yeah, this is just one of the graphs from the paper where you're just kind of seeing running 128K context wasn't possible before. With the MacBook 64 GB, it used to take this much RAM, and so we made it take 40 gigs instead. And so it was very, very fun and interesting to see, especially on something that's consumer hardware. So thank you so much.
Any questions? Yeah, Dan.
Should I speak into the thing, or can you hear me from there?
We can hear you if you like yell.
Come a bit closer. Yeah, I had I guess 2 questions really. First of all, I think I saw, did you have some way of verifying that the work that these agents did or these different people did Did you have a way of verifying that they actually did that work, or was it all just based on trust?
Yeah, that's a great question. So for the Autoresearch project, it was based on trust, and like we actually have backgrounds. We all work together in distributed systems, and like we built like ZK systems before, so we have thought like pretty deeply about adding like verification for like future public experiments. Because yeah, it depends like what the actual like agents go off and figure out and what they want to run. The way that we were able to sort of like tighten it was just by like clearly defining evaluation harnesses. And so like that would be able to like clearly reject stuff. But Sai, I'll pass to you if you have anything you want to add to that.
Yeah, just two things. One, for the Apple kernel experiment, the baby solution to this is only have people you trust work within a within a harness, and then for the my version that we did recently for this paper, that was just all independent. We had our own agents running on this system internally. Yes, we have many ideas on how to verify this, and I think it's difficult to not turn this into like some sort of complicated distributed system task management type of problem. But yeah, very very interesting way of like basically very very interesting move forward, I think, in improving in that sense.
And then I guess follow up, once you can verify it, did you think of any way of like reimbursing all the people who contributed in some way, or making some economic sense of it all?
Yeah, there's like I guess like you can have like tensor block style like economic incentives and stuff if you want. Like it ends up looking like a blockchain really quickly. The challenge is that like if you're renting GPUs, like it's just like a unit economics problem, right? Like you have to basically pay for the compute and then pay for some incentive on top of that. And so yeah, we didn't get there for this problem. Like most of the people that joined that were actually just interested in contributing, like just to see the numbers go down. And so where we see it also going is like if we use like that Mac inference example, like for instance, the people that would benefit from faster inference are people that have specific devices. And so if you're in the set that would benefit from having lower inference, then it actually may make sense for you to contribute to it. And if enough of you contribute to it, you can actually get the model that you can run yourself, right? So like there's some interesting incentive structures, but we have just haven't gotten there yet.
Very interesting, thanks.
All right, any other questions? Maybe one more question. Yeah, go for it.
Do you use NPU feature on the Mac?
I couldn't hear that. Could you?
Do you use the NPU processor at all?
Yeah, so he's asking if you use the neural engine, the NPU.
In which experiment in particular?
Putting the Lambda in the 64K.
Yeah, putting the llama in the 64K.
Oh yeah, this was a pure like metal kernel, so no A&E, like just no Apple neural engine. It was just bare metal like GPU on the Mac, the 32 core GPU you get on the M1.